So let's look at maybe a couple more transformations. Notice this one has more than one transformation going on. You might even prefer to switch that x and the 1. If you wanted to call it log base 2 of x plus 1 plus 2. Hopefully you kind of recognize what will happen here. The plus 1 is with the x. You would think it would move right 1, but it's really going to move left 1. And then the plus 2 is not in there with the x, so it's going to be something vertical. It's going to shift up 2 units. So I'm thinking I can almost draw this just kind of an approximation freehand here. Now they do want us to get a table from our calculator and plot a little bit more accurately, but I've got a pretty good sense of what's going to happen. Remember that key point 1, 0. If that key point at 1, 0 moves left 1 and up 2, I'm predicting right now that 0, 2 is going to be a point on this graph. And normally I have a vertical asymptote at x equals 0, but if I shift this whole thing left 1 unit, I bet that vertical asymptote goes to -1. So I bet this graph kind of goes up to the right here and then drops on the left towards that -1. But let's look at the graph just to see. If you have an 83, you're not going to be able to graph this yet. I'm going to show you a trick in a little bit. If you have an 84, you will have to change the log base. You can't just hit the log button. You're going to have to tell that you want the log base 2. So hit the math button and arrow down to the log base. And that's where you can tell it that you want the base to be 2, that you want your argument to be 1 plus x or x plus 1, and then arrow out of the parentheses to hit the plus 2, okay? And if you look at your table of values, okay, notice a bunch of these say error. We'll talk about that in a second. So I'm going to write -1, error. That means nothing's there. 0, 2 is a point. That's the one that we predicted, right, was 0, 2. 1, 3 is a point. 2, 3.585 is a point. 3, 4 is a point. And we could put some more, but I think that's enough to kind of get us going. Okay. So there was our 0, 2. Here's our 1, 3. Here's our 2, 3.5 approximately. And there's our 3, 4. So the curve, it goes kind of up to the right, and then it will drop on the left, approaching that vertical asymptote of x equals 0. Okay? Now notice, why does it say error for all these values on the left? The reason it says error is that once we get past -1, there's nothing there. It's not part of our domain. Okay? Remember, our domain was normally 0 to infinity, or now that we move that, shifted this graph 1 unit to the left, it would be -1 to infinity. Okay? So just kind of wanted to point out that your calculator will say error message in your table for any values of x that don't work, for anywhere that the graph does not exist. Okay? All right. These next couple, they've given us not only the equation but also the graph. That was nice of them. Okay? And they just want us to come up with the domain, the range, and the vertical asymptote. Okay? Well, looking at this one, looks like, and again I'm looking at my equation here, looks like this regular function, a log base 2 of x, went left 3. Okay? So that point that used to be at 1, 0 went left 3 units, is now at -2, 0. That vertical asymptote that used to be at 0 went left 3 and is now at -3. Okay? That's where it kind of has that imaginary line that the graph approaches but doesn't touch. Okay, so the domain for this guy normally would be 0 to infinity, but since we shifted it left, it's going to be -3 to infinity. The range is still -infinity up to +infinity. And then where is that vertical asymptote? That vertical asymptote is x equals -3. Okay? All right, this one. Notice it took our regular log base 2 of x function, and it flipped it vertically, not horizontally. The negative is not with the x, so it wasn't a horizontal reflection. It's vertical. So that key point at 1, 0 is still there. But instead of traveling up to the right, that part flipped down. And instead of dropping quickly on the left, that part flipped up and it's going up quickly. Okay? So the domain of this guy is still 0 to infinity. The range is still -infinity to infinity. It goes down forever and up forever. and our vertical asymptote is still at x equals 0. It's that same location. Okay? Now, why are we kind of thinking about domain and range so much? Well, I haven't mentioned this yet, but the argument of a logarithm must be positive. What do you mean the argument? Well, remember, argument was not the base number, but it was the number over to the side. Okay? So when we're in log form, the base was right here next to the log, but the number beside it is what we call the argument. Okay? Arguments must be positive. They have to be greater than 0. Now think about why that is. Let's say, remember we had 2 to the third equals 8, right? So log base 2 of 8 equals 3. That exponent is what's over by itself once we get to log form. The 8 is our argument. So notice in log form, the argument is right here. It's next to the log part, not the base, but part next to it. In exponential form, the argument is the part that's by itself. So if we have to have positive bases, remember we can't have a negative base in an exponential. If I have to have a positive base, is there any way I can raise it to some value so that I get a negative number over here? Well, no, because if I put a negative exponents just mean 1 over whatever that is. It does not actually change the sign to negative. So there's no way that we're going to be able to get a negative argument. There's no way this number over here next to the log base whatever can ever be negative. Okay? Has to be positive. When we went back to our graph of y equals, let's clear that one for just a second, log base x, the graph only existed for positive numbers because in that case, the x value was the argument. The argument had to be positive numbers. The graph only exists when that argument number is positive. So whatever we have in the argument position has to be greater than or equal to 0. So in this case, our x minus 2, that's our argument, it has to be greater than 0. So when I solve this to get x by itself, I add 2 to both sides, I get that x is greater than 2. So that tells me that the domain of this graph, x is greater than 2. That means it starts at 2 and it goes to infinity. If you want to verify that by checking the graph, again, they want the log base to be 3. So I'll hit math, arrow down to log base, tell it I want the base to be 3. And type in my x minus 2. And when I graph it, sure enough, it shifted that graph to the right 2 units. So the vertical asymptote that used to be at 0 is now at 2. So our domain is 2 to infinity because that minus 2 shifted the graph right 2 units. Okay? For this one, whatever's in the argument position, in this case 1 minus x, has to be greater than 0. Okay? Now, I could move the 1 and then get rid of the negative, but I think it'd be faster just to move the x, add x to both sides, and get 1 is greater than x. Well, if 1 is greater than x, that means x is less than 1. So that means our domain is negative infinity up to 1. Your domain can go up to 1, but not higher. If you graph that one, math, arrow down to log base 5 of 1 minus x. And when I look at my graph, this is a new twist. It started on the left and it goes to the right. And it looks like at positive 1 is where that vertical asymptote would be located. Okay? For this one, our argument is x squared. The argument has to be greater than 0. Okay? This is a quadratic, so to solve it, I'm going to take the square root, and I'm going to get x is greater than, or, well, actually I run into an issue here. X squared is greater than 0. Now, if you think about this for a second, rather than take square roots, would you agree that no matter what number I put in for x, it's going to come out positive? If I put in a positive number and I square it, I'm going to get a positive number, something greater than 0. But if I put in a negative number and square it, that's also going to come out positive. So anything squared comes out positive. Except for 0, because if I square 0, I get 0, and 0 is not greater than 0. But other than 0, anything will come out positive. So that means our domain is negative infinity to 0, union 0 to infinity. The only thing I'm kicking out is 0. And the reason I'm kicking out 0 is because if I square 0, I get 0, not something greater than 0. Okay? Remember, our argument had to be positive. So x squared has to be greater than 0. It can't equal 0. Okay? If you look at that graph, this one looks interesting. My base is 10, so I can hit the regular log button, x squared, and when I graph it, there's our picture. And it's kind of hard to tell that it doesn't exist at 0, but if you look at the table, when x is 0, it says error. So that's why 0 was the only number it couldn't be. Okay? All right, let's try a few of these conversions. Remember, here's our reminder how to convert. If you're given an exponent, log base, whatever that exponent was, if you're giving an exponential, the base of your exponent is the base of your log. So this would be log base 2. The whole point of logs is to get an exponent by itself, so the 3 is what's by itself, okay? And then the 8 over here is your argument, okay? All right, so they are asking us to write each of these equations in exponential form. Now notice what's happened. They are giving us log equations, and they are asking us to convert them to exponential. So the base of my exponent is the base of the log. So if 4 is the base of the log, it's going to be the base of the exponent. The whole point of logs is to get the exponent by itself. So 2 must have been the exponent, and then my argument must be what's by itself in exponential. Hopefully you agree that 4 squared is 16. Okay, 4 to the second power is 16. And that is just a different way of saying log base 4 of 16 is 2. Okay. In your calculator, if you want to practice this, I'll show you how to type this in your calculator. If you're using an 84, hit the math button, arrow down to log base, and you can fill in the blanks. 4, 16, and it's going to say, oh yeah, that's 2. Okay? And hopefully then you can say, oh yeah, I agree with that because 4 to the second power is 16. You can see that those are equal statements. Okay? Now, just so you know, if you're using an 83, you do not have that log base feature in your calculator. So I'm going to show you a little trick. You won't understand why right now, but in 4.4 we'll show you why. If you will type, if you're using an 83, you can hit log, there's no log base feature for you in an 83, but if you'll hit log of 16 divided by log of 4, that will come out as the answer of 2. Okay, and we'll explain why that is in 4.4, but if you're using an 83, you don't have that log base feature. So you could type log of the argument, so 16, divided by log of the base 4, and it'll tell you that was 2. Okay? All right, all they asked us to do here was convert. All right, so I'm trying to convert this one. So it's a log, so to convert it, I want it to be an exponential. Well, the base of my exponent is the base of my log, so 5. The whole point of logs is to get the exponent by itself, so my exponent must be negative 1, and that must equal 0.2. Hopefully you agree with that. Hopefully you agree that 5 to the negative 1 is 0.2. But if you didn't, remember, what does a negative exponent mean? Negative exponent means stick it on the bottom. Well, what is 1/5? It's 0.2, so that was correct. Okay. All right, another one, they've given us a log. They just want us to convert to exponential. So the base of the exponent is the base of the log, so I must have 8. Whole point of logs is to get the exponent by itself, so 0 must be the exponent, and that must equal 1. And hopefully you agree that that's a true statement. Anything to the 0 is 1, so 8 to the 0 is 1. Yeah, that works out. Okay, another log, base of the exponent is the base of the log, so 23. Whole point of logs is to get the exponent by itself, and sure enough, that's true. 23 to the 0 does equal 1. Okay. Now we're doing the reverse. Now they're giving us exponentials, and we're asked to convert to logs. Okay. Remember, the whole point of a log is to get the exponent by itself. So we know the 4 is going to be what's by itself. The base of the exponent is the base of the log. So log base 2 of 16 equals 4. Okay. These mean the same thing. It's just that one's written in exponent form, one's written in log form. Okay. Both of these statements would work out the same in a calculator. If you type 2 to the 4th, it's going to tell you that's 16. And if you went to log base 2 of 16, the calculator is going to tell you that's 4, because these are two different ways of saying the same thing. Okay? Log base 27 of 3 equals 1/3, because the whole point of a log is to get the exponent by itself. And again, if you typed 27 to the 1/3 in your calculator, it would tell you it's 3. If you typed log base 27 to 3 in your calculator, it would tell you it's 1/3. Okay? Remember, if you do not have an 84, if you're using an 83, you would have to say log 3 divided by log 27 in order to get the 1/3. 0.3 repeating as 1/3. Okay. All right. Last one here. Log base 1/4 of 16 equals -2. Hopefully you agree with that statement. Remember, a negative exponent means flip it over. So if I flip over the 1/4, I would get 4. I've flipped it over, so the negative done its job. It's just 4 squared, and that does equal 16. So hopefully you agree that that is a true statement. Okay. This next group, they ask us to evaluate. Evaluate means work it out. See what number is equivalent to it. So they want us to evaluate log base 12 of 144. They want to know, hey, what number does log base 12 of 144 equal? Okay. Now, you have a calculator. You could totally type that in. Okay. If you have an 84, you can hit the math button, arrow down to log base, and you can say, oh, log base 12 of 144, and it'll tell you that that answer is 2. If you do not have an 84, if you're using an 83, you can hit log 144 divided by log 12. I know that's weird. We'll see in the next section why that's how you have to type it in. But you could type log 144 divided by log 12, and it's going to tell you that's 2. Okay? So I know you could type that in a calculator and get that the answer is 2. But I want you to see if you can think about it on your own and come up with what that answer is. Remember how we said logs and exponentials are the same thing. They're just different ways of writing it. Okay? So what if I convert this from a log to an exponential? Well, remember, the base of the exponent's the base of the log. So this is saying that 12 to the something is 144. Okay? How do I know that the 144 is what's over here? Well, remember, the whole point of a log is to get the exponent by itself. So whatever was by itself in log form must have been the exponent. So what should I put in this little blank so that 12 to that number will equal 144? Oh, 2. 12 squared is 144. That's why log base 12 of 144 is 2. Okay, let's try another one. Log base 64 of 8 equals something. We don't know what that something is, but we know it equals something. Okay, well, 64, that's our base, to the something has to equal 8. And this one I had to think about for a second, okay? What could I raise a 64 to? What power could I raise it to so that I get 8? And I thought, well, the only way I know of that 64 turns into 8 is if you take the square root, because square root of 64 is 8. Well, remember that square root is the same thing as raising something to the 1/2. So 64 to the 1/2 is 8. Because the square root of 64 is 8. Okay, so that means log base 64 of 8 is 1/2. Okay, and you could verify that. You could type in your calculator log base 64 of 8, and it'll tell you that that's 0.5. Okay, all right, next one here. Log base 3 of 1 over 27 equals something. We don't know what. So 3 to the something has to equal 1 over 27. Now, I'm pretty sure that this is going to be a negative number because I know that if you have a negative exponent, it sends that thing down to the bottom. And I also know that 3 times 3 is 9 times another 3 is 27. So I bet you this is 3 to the negative 3. Okay? In fact, if you type 3 to the negative 3 in your calculator, it gives you a decimal, but if you convert that to a fraction, you do get 1 over 27. Okay? If you went to math, log base 3 of 1 over 27, it will tell you that that answer is negative 3. So we were correct. Remember, if you're using an 83, you would have to hit log of 1 over 27 divided by log of 3, and it will give you that correct answer. Okay? Okay, we mentioned earlier that log base 10 comes up a lot. In fact, we just gave the log button, we gave just regular old log, its own button on the calculator, and whenever we hit this log button, it's implying that the base is 10. You have to go into the math and choose log base if you want it to be something other than 10, okay? So log base 10 comes up so often that we say, you know what, don't even put the 10, just write log, and we'll know that the base is 10. We call that a common logarithm. Another one that comes up a lot is log base e. It comes up so often that we said, you know what, don't even worry about writing the e, just put ln, okay? Now, we had to put ln, we couldn't just use log because log was already taken for base 10. So ln stands for natural log, and it's just saying, hey, your base is e. It means log base e, okay? Except we gave it its own button on the calculator, the ln button, okay? So those come in handy. Okay, so when they ask us to evaluate log 100, it's kind of like what we just did. Log base 12 of 144 is something, so log 100 is something. You just have to recognize that the 10 is missing. They didn't write it, but it's there. So this means 10 to the something had to equal 100. Oh, well, I know that 10 squared is 100, so I bet log 100 is 2. And it is. Okay, and in your calculator, if you type log 100, it's going to tell you that that is 2, because it knows that you meant 10 to the second is how you would get that argument of 100. Okay? All right, same thing here. We know the base is 10. 10 to the something has to equal 0.0001. All right, well, what could we make that exponent? What could it be? I bet it's going to be negative, because remember, we're going to a smaller number, okay? And this 0.0001, the 1 is in the 10,000ths place. This 0 is the tenths, the hundredths, the thousandths, 10,000ths. So this number really means 1 over 10,000. So I bet you this is negative 4. I bet you that 10 to the negative 4 would give us the 1 over 10,000. Okay, scientific notation. But if you typed in log 0.0001, it is going to tell you that it's negative 4. Okay, so 10 times 10 was 100, times another 10 was 1,000, times a fourth 10 was 10,000. And we had to make it negative to stick that 10,000 on the bottom. Okay? All right, this one. Now, what the heck? What's going on here? Well, it just says ln. We know that means log base e, okay? So even though there's another e right here, this really is saying log base e of e to the negative 3. That's really what this is saying, okay? So if we start from this e, just like we started with the 10 that wasn't written but we knew it was there. We start with the e that isn't written but we know is there. E to the something has to give us e to the negative 3. What should we put in that blank? Oh, I bet it's negative 3. Okay? And in your calculator, if you would hit ln of e to the negative 3, it will tell you that that answer is negative 3. Okay? Later, we're going to learn that if you have an exponent in your argument, that exponent can really just get pulled down in front. So you'd have negative 3 ln of e, and we're going to learn that anytime the base and the argument are the same, that cancels out and leaves 1. So that would be another reason that it's negative 3. But we'll get there. Okay? All right. Number 14 here. They put e to the 10th, but there's another little base of e right here. So whatever that base is, that little e that's down there in the base, raised to the something, has to equal our argument of e to the 10th. So what should go in this blank? 10. So I bet ln of e to the 10th is 10. ln of e to the 10th, and sure enough, it's 10. Okay? We can also work with our calculators. So far, all of the examples have worked out nice, like 12 squared was 144, 64 to the 1/2 was 8. But sometimes it doesn't work out so nice. Sometimes the numbers come out a little messier. For instance, log 43. Okay, if I just type log 43 in my calculator, it's a terrible, horrible decimal. And really, it goes past the 6 that they gave us. My calculator just ran out of room. What that really means, remember, they didn't write the 10, but we know the base here is 10. 10 to the something had to equal 43. Well, 10 to the first is 10, 10 to the second is 100, you're never going to get it 43 exactly. But I bet it had to be 1 point something, because if 10 to the 1 is 10 and 10 to the second's 100, I bet it's 10 to the 1 point something. And that's why this decimal came out to 1.635 whatever. If you want to check it in your calculator by saying 10 to the 1.6335 or whatever, you don't get 43 exactly, but it's very close. It's close enough with when you consider the rounding, okay? All right, so what this is saying right here, log 200, 10 to the something has to equal 200. Well, there's not going to be a whole number that will multiply, that we could put in there, that 10 to that number will be 200. So it's going to be a decimal, okay? And I bet it's 1 something, because 10 squared would be 1,000, and that would be too much. So in your calculator, if you type log 200, it's going to give you a decimal. 10 squared is 100, sorry. 10 to the third would be 1,000, and that would be too much. So it's going to be 2 point something. So, and then just round to whatever place they say. They said 4 decimals. So we'll say 2.3010. And I do need that O because without it, it's going to look like I didn't follow directions and round to 4 places. Okay? As a check, 10 to the 2.3010. It's not exactly 200, but if you rounded it, it'd be 200. Okay? All right, so you're going to need a calculator for this little group right here because you can't type it in. Okay? All right, log 0.074 is going to be negative 1.1308. Okay? ln of 200. Keep in mind that means e to the something equals 200, and it's going to be that 5.29 number. So if you think about e raised to the 5.2983, you get real close to 200. If you rounded it, you would get 200. Okay? And then ln 1.005 is 0.00, let's see, 50 is what that would have to round to. Because the 4th decimal is a 9. So if the number after it, where the 8 is, tells that 9 to go up from 9 is 10, so it's going to carry that 1 into where that 4 is and make it a 5. Okay? And I think that's a good spot for us to stop on this video. We're going to get into a few properties in the next one that will be useful as well.